just begin with acknowledgement of country. We're gathered here on the lands of the Wurundjeri people of the Kulin Nation. We pay our respects to elders past, present, and emerging. Lands remain ceded. Today, we are hugely privileged. Look at those. To be in the presence of Dr. Daniel Bennett, who
don't do this.
So Dan started with a PhD at Melbourne here in the Decision Neuroscience Lab. Did a postdoc at Princeton, then proceeded to a lectureship over at Monash. And we're hugely fortunate that in November, he'll be joining us here at the School of Melbourne.
I'm very lucky,
So Dan's research focuses on cognitive decision making, but specifically, as of lately, gambling decisions. But not the kind where you take money from the gambling agencies.
That's right. Yeah, they haven't offered it to me yet.
Not yet. When they do.
It's easy to be honourable when you don't have the opportunity to be dishonourable.
And today, he'll be telling us about risky decision makings in the wild, the case for studying decision making in real world gambling products. Thank you, Dan. Okay.
Thank you very much for the very kind introduction. Thank you, Andrew, for the invitation to talk. I feel like I'm wearing out my welcome at this talk series a little bit. I spoke, I think I looked up in April last year. So I thought I would talk today about something completely different to what I talked about then. So what I talked about 18 or so months ago is some sort of theoretical basic science work about how we can understand decision-making a little better if we understand how subjective emotions fluctuate and influence the decision-making process. What I'm going to be talking about today is sort of the other half of the research that I'm most interested in, most engaged in at the moment, which I sort of think of as being the applied component of that research. So cognition and emotion is something that happens within our laboratory tasks, but there's one really prominent real-world place where this happens as well, which is lots of real-world gambling products. So I have been studying this for 3 or 4-ish years now. The impetus for studying this was I arrived back from the United States in mid to late 2020, and as I like to do, I watched a lot of Australian sport, and I was shocked and surprised by just the prevalence of gambling advertising. And it made me think that perhaps, being someone who studies decision-making under risk, I might be able to develop a line of research that could intelligently say something about this, obviously very prevalent and culturally central part of Australian culture. I should say this a minute ago, because of some unfortunate scheduling conflicts, I'm going to have to run off pretty strictly at 5 minutes to 12. But Christina Van Heer has been kind enough to donate her desk to me for the afternoon. So after lunch, I'm going to hang around on the 8th floor. And if anyone would like to continue conversations and chat, then please do stop by. Okay, so what the talk today is going to be about is this. It's going to be 3 parts. I'll try and do it about 15 minutes or so each. In part 1, I'm just going to sort of generally lay out the perspective that I've adopted in this research. I'm going to talk about why it's beneficial both for the implied impact of psychological research, but also for theoretical advances in psychological research to study the sorts of gambling products that exist in the real world. And then I'm going to go on to 2 specific cases where I've tried to bring these principles into practice. One involving a certain kind of outcome called near misses that occur within slot machines, poker machines, and the other one involving a feature that's existed in sports betting apps for the last 10 years or so called instant cash out. But I'll try and give the sort of the big picture view of this first of all. So, all right. So I think as a starting point for this, especially for people who consider decision-making and cognitive psychology from a sort of basic science theoretical perspective, it's helpful to know that when we think about advances in decision theory and probability theory, for centuries, theoretical advances have gone hand in hand with the study of real-world games of chance. So you can take this back a long way. You can take it back at least until the 17th century, where Blaise Pascal and Pierre de Fermat invented it's not too much to say, invented the conceptual foundations of modern probability theory, including such things as the notion of an expected value within some letters that they sent back and forth to each other, where they tried to work out, if we're playing a game of dice, that has a number of rounds, and the game is interrupted after some number of rounds, how should we fairly split the stakes so that nobody is disadvantaged? And from that grows a very large amount of work, of course. It's not just in the 17th century. So in 1928, John von Neumann published a paper called The Theory of Parlor Games, where he considered the question of whether one should bluff when playing poker. It was well known that people did bluff when playing poker. The question he considered here was whether it was in any way advantageous to do so. And with this 1928 paper, and with a later book in the 1940s with Morgenstern, he laid the foundation for sort of modern game theory by considering whether one should bluff in poker. There's other examples as well. Here's another one I like. This is part of the Manhattan Project. So Stanislav Ulam, the physicist, invented or at least was inspired by a difficult computational problem and developed methods that we think of now as being the basics of things like Markov chain Monte Carlo methods. So what Stan was interested in answering was, if I lay out a set of cards in solitaire, in some ways, if I play perfectly, there's some probability that I will be able to get that game out, and there's some probability that I won't be able to get that game out. That's combinatorically, to try and calculate those probabilities is really, really hard. That's a really complex problem. In the story, as I've heard it, Stan Ulam was someone who did not really enjoy doing lots of complex calculations. He was more of an ideas guy. And so he thought, well, what if rather than actually doing the exhaustive calculations, what I could just do is just lay out lots and lots of solitaire games. And the average of the number of times they come out by chance will converge on the probability. And this insight gets taken up in the Manhattan Project, and firing neutrons and physics things at things, but it arises in some ways out of the consideration of a game of solitaire. Here's a quote from Pierre-Simon Laplace, always good for a quote. It's remarkable that a science which began with the consideration of games of chance should have become the most important object of human knowledge. I'm not sure everyone would agree it's the most important object of human knowledge, but this is the sort of the general angle here, is that for a long time we have developed conceptual insights from studying the ways people behave, and the sort of the mathematical probabilities within games of chance. Okay, however, if we look at the contemporary study of risky decision-making and the sort of cognitive psychology, economics, broadly the judgment and decision-making research, what we see is that there has, at some point in the last 30, 40, 50 years, been a divergence between the sorts of gambles, the sorts of decisions that are studied by academics, and the sorts of gambling products that exist in the real world. So here, this is one depiction of sort of one of the standard sorts of ways in which gambles are presented to people in the laboratory in the study of judgment and decision-making, or in the study of risky choice under that umbrella. So what you're choosing between here is gamble 1, which has 50% chance of paying you 100 euros and a 50% chance of you losing 50 euros. Or you can choose gamble 2, which has a 65% chance of losing 40 euros and a 35% chance of gaining 340 euros. There are a very great deal of really quite sophisticated, really quite lovely theoretical work has grown up around explaining the ways that people behave in decisions like this. I don't mean to denigrate that work in any way. It's very important work. But the observation I would make is that if this product existed in a casino, nobody would play it. If you're in a casino and you can sit at a table and play this game, or you can go and play blackjack, you can go and play the slots, you can go and play poker, you're going to choose to do one of those things instead. This is not a product that exists in the real world. To drive this point home a little more, I'll show you a couple of videos just of what sort of relatively standard decision-making tasks assessing risky decision-making look like. And as I'm doing this, I just want you to be sort of thinking about the sorts of gambling products that you know to exist in the real world and how they don't really look like this. So this is a classic, 30 years old now. This is the Iowa gambling task. So here, we play the video. Here you choose a series of decks. On each deck you have a gain amount and you have a loss amount. So I win $50 and I lose nothing. I win $50 and I lose $250. I win 100 and I lose 0. And over time, depending on the way in which I'm making my decisions, I converge on some representation of the values of these different options and I choose advantageously or not. It has cards, so in that way it sort of resembles something that exists in the real world, but again, this is not a real world gambling product. And though we can learn a lot about decision making from studying this, there's something that is left out. Just to be clear that I'm including my own sort of work in this criticism. Here's a way in which some of my work, some of the stuff I presented at the Complex Human Data Hub last time I talked, kind of falls within exactly this. So here's, you're choosing between two cards. Here you have a 25% chance of winning 10 points and a 75% chance of winning 2 points versus same probabilities of winning 2 and losing 10. And what a person might do is sort of repeatedly make some choices. So they choose the one on the left, they win 2 points. They're presented with a different set of options. Here they choose the one on the left, they lose 10 points, etc., etc. So, you know, this is the sort of thing that we very commonly study in the study of risky decision making. And so Ralph Hertwig has made the point that in some respects, what we have here is a sort of a model organism. So in the same way as if you study genetics, historically, it has been very helpful to study a model organism like the lesser fruit fly, Drosophila melanogaster, because it's very tractable to study in the laboratory. You can get lots of generations of fruit flies within a small amount of time. Some of the basic principles of genetic selection apply in fruit flies as much as they do in any other organism. And so we can learn some really beneficial things from studying Drosophila. Well, what Ralph Hertwig would argue, and what I agree with, is that what we have when we look at these sort of risky choice tasks is a kind of judgment and decision-making Drosophila. Really useful to study, really convenient, really tractable, but we would be making a mistake if we extrapolated completely from behavior on this task to behavior in real-world gambling tasks, gambling products, in the same way as we can see that it would be an error to sort of extrapolate everything that we know about fruit flies to human genetics. There's lots of things that we can learn, but there's also things that are left out anytime we have a model organism or a model task. So why should this bother us? Why should this concern us? I would say that there's 2 reasons why we might want to pause and think about what's left out when we consider these real world when we don't consider these real world games of chance. So the first argument is sort of an applied benefit argument, which is that our standard theories of risky choice that are developed using these model tasks, they don't generalize very well to real world gambling decisions. We kind of know this. They are designed to study stylized decisions. And that's fine. They're very elegant, very sophisticated. But what that means is that if someone from the Victorian Racing Casino Control Commission, I think the acronym is, were to email me as a decision-making researcher and say, there's this new gambling product, what do the theories say about how we should regulate it? The only honest answer would be, I don't know, the theories don't apply to that product. And so if we would like to be able to make representations meaningfully to policymakers and to ideally to reduce gambling-related harm from the products that exist in the community, we would like some way to extend the theories that we have to encompass more realistic gambling products. There's another argument you can make here, which is the sort of the basic science argument, which is, okay, let's imagine that you're a cognitive psychology researcher who doesn't care about the real world. That's completely fine. But we're actually missing the opportunity to improve our theories here as well. By focusing on a really narrow set of decisions, we abstract away a lot of the things that exist in the real world, and we miss the chance to learn from the ways that people behave in the real world. So lots of real world behavioral phenomena, we can imagine using them to extend our theories. We can imagine using them to constrain our theories. Basically, if our goal is just to write the perfect equation that describes risky decision-making, and I think that's a fine goal. I have days where I wake up and that's, I think, my goal. Then it would also be advantageous to consider these products because they provide lots of information that we're throwing away if we don't consider them. So as a jumping off point, what we have to, what's helpful to consider is how do standard models sort of conceptualize risky decision-making or value-based decision-making? And I'm going to caricature this to a large extent. So if this were a combative audience, I would think I would probably get stuck on this slide for half an hour. So please know that I'm leaving lots of things out here. But if we think of sort of one dominant framework, the stuff that some of the neuroeconomics type folks employ, we end up with a sort of a box and arrow model that looks kind of. So first, when we're given a choice between 2 options, we have to appraise those options. We have to combine information about outcome magnitude and outcome probability into some representation of how good it would be to choose each of those things. We have to have some action selection process. We have to translate whatever representation we're working with into a decision, an action. We have to evaluate the outcome. It's fairly straightforward in this case. The outcome is just X2, but in other cases, it might be more complex or it might be multidimensional. And then optionally, we may have change in our preferences. So if we're in a sort of a decision from experience, reinforcement learning type framework, then perhaps the evaluation of this outcome changes the preferences that we have and the way we appraise things the next time around. Each of these boxes, you know, is a field of study. And again, I want to make clear, it's not my goal to denigrate any of this. It's just my goal to think about, if we wanted to expand on this framework to consider the sorts of gambling products that exist in the real world, where would we, what extra boxes and arrows might we need? So that brings me to the first of the two empirical studies that I'm going to talk about, which is this phenomena that I'll describe called near misses in slot machines. And what I'm going to try and get to is, how might we extend a framework like this one coherently to account for the sorts of experiences that I'm going to describe people having. Okay, so because we are talking about a real world gambling product, I'm not going to assume any background knowledge here. Let me talk to you a little bit about slot machines, also called like electronic gaming machines or gambling machines, also called poker machines. So Australia has about 0.5% of the world's population, but it has about 20% of the world's slot machines. If you just did a census, 10% of the world's slot machines would be in New South Wales. That's pretty high. Australia also, probably not coincidentally, has the world's highest rate of per capita monetary gambling losses. So on average, Australian adults lose $1,200 per year. And that's 50% more than the next worst country. And about 80% of those losses come from slot machines or from poker machines. So if we want to approach this from the point of view of reducing gambling-related harm, we would want to start with the most harmful products, and it's the research is clear that slot machines are probably the most harmful product. One reason why they're a harmful product is because they have all sorts of features that are, I'm quoting Natasha Dow-Schull here, I haven't cited her, addictive by design. So slot machines have, going back to the language of behaviorism, have a variable ratio reinforcement schedule, which is they pay out in proportion to the number of responses that a person makes. So if you sit there and play a slot machine, in the long run, you should expect to see a win with a certain proportion of times, but it's a variable ratio. So it's not just every 10th play you win, it's sort of unpredictable in some deep way. So since the days of behaviorists, we've known that variable ratio reinforcement schedules kind of screw with organisms' decision making. So Skinner and the Skinnerian school showed that it is possible to design a variable ratio reinforcement schedule for animals such that the animal will expend more energy pressing a lever or doing whatever task they're being asked to do than they are receiving on average from the food that they receive from those actions. And so in some ways, we are dealing with an extension to money of the same sorts of principles. But it's not just that they're a variable ratio reinforcement schedule, and I think this is the important point. If you play a slot machine, you don't just press a button, it says lose, press a button, it says lose, press a button, it says lose, press a button, it says win. You are presented instead with quite a sophisticated array of things that happen. So I won't go through all these things. There's things like multi-line play, there's auto spin, there's bonus rounds, there's double or nothing bets. Dan Miles has done a lot of really nice work studying losses disguised as wins. And the focus that I'm going to be talking about here today is near wins, or I'll use the term near misses as well, interchangeably. So I won't show you a near miss straight away, but I will just give you a sense of what multi-line poker machine play looks like for those of you who have been fortunate enough not to be exposed to this. So this is a screenshot or a screen grab of what you might see if you're playing a poker machine. So that's one play, that's a loss. There's another play, that's a loss. There's another play, in spite of the animations, that's also a loss. That's another loss. So what I want to point out here is that there's something going on in this bewildering array of things. So there's a sequential array of things. There's lots of lines along which basically what you're looking for is 3 in a row across the first couple. If you get 4 in a row or 5 in a row, all the better, you win more. So if you were to get queen, 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 there would be some payout associated with that. So if we go back to our standard model, in some basic way, what is missing from this model that we want to extend to account for real world phenomena? Well, one way of thinking about this is just that this isn't just an arrow. There's a prolonged delay here between selecting the action and viewing the outcome of your decision. In these slot machines that I just talked about, it's only 4 or 5 seconds, but in risky choice more broadly, it can be almost arbitrarily long. So I can, if I want, buy a ticket for the lottery on the weekend today, and I have to wait a week before I find out the outcome of that lottery. So there's, okay, I haven't done anything revolutionary here. I've just drawn a longer arrow. You can hold the acclaim, but the point I'm making here is that there is often a prolonged delay between this point where you select an action and this point where you view the decision outcome, and that may seem like a trivial thing, but actually one interesting thing that happens during that delay is that you can view informative signals. So what's happening if we go back here and I play this video again? Every time I play this, I view a set of signals that provide sequential information to me about whether I have won or not. And that sort of bridges the gap between selecting an action and knowing the outcome of that action. So it seems like this, you know, in some standard conceptualizations of the decision process, this feels like it should be irrelevant. It feels like, you know, there is a cognitive process going on here. There's a cognitive process going on here. Cognitive process going on here, but here there's just things that we view that we can't do anything with. We're getting information, but can't do much with it. But what I'm going to argue is that incorporating some sort of an appreciation of what's going on here may give us a better understanding of what's going on in real world gambling products more broadly. So the specific phenomenon that I'm focusing on in this line of research is something called a near miss. It's been known for a very long time to be part of slot machines. So I'm showing much more simplified slot machines here. So on the left, from by Siskus and all from 2016. On the left, we have an example of what a near miss might look like in a slot machine. So here you have to get 3 7s in a row in order to win. First reel is a 7, the second reel is a 7, third reel, oh damn, you can see it's almost a 7. On the right, you have an outcome that is numerically equivalent in the sense that you don't win anything for either of these, but doesn't give you the sense of you know, almost having experienced a win. So slot machines produce these. They produce them at higher than charts rates. The regulations say that then you're not allowed to explicitly show near misses, but people like Charles Livingston, who do great work. Charles did the study where he bought a secondhand poker machine and he hired someone to look at the circuit board and he extracted the estimates of what's going on in all of these. The ways that contemporary slot machines do this is not by explicitly showing you what would have been, but loading win symbols on the first 2 and then having relatively few win symbols or more symbols in general on the third reel. So actually, it's designed to make you feel as though there's equal numbers of symbols, but there might be 10 symbols here and 10 symbols here and 35 symbols here. And so that produces near misses at higher than chance rates. And what it has been shown that they do is that if you play a slot machine that frequently generates near misses, you have increased resistance to extinction of your gambling behavior. So if the slot machine stops paying out, you will play for longer if you have seen some near misses than if you haven't. And people, if they're asked how motivated they are to continue gambling, we'll say that they are more motivated to continue gambling on these machines that generate near misses. That's sort of, in some ways, established fact, although I think the evidence base is a little weaker than is sometimes claimed. The question that I want to ask here in this project is, what is the cognitive process? What is the cognitive mechanism by which near misses have this effect on behavior? So there is a dominant hypothesis in the literature, which dates back to Skinner in the 1950s, writing about near misses, which is conditioned reinforcement. And so to explain this, I'll quote directly from Skinner. For example, the standard slot machine reinforces the player when certain arrangements of 3 pictures appear in a window on the front of the machine. By paying off very generously with the jackpot for 3 bars, the device eventually makes 2 bars plus any other figure strongly reinforcing. So the argument here is that 3 7s is a strongly reinforcing display. 2 7s looks quite a lot like 3 7s, and so there's sort of this generalization process by which the incentive value of the win display generalizes to things that look like wins, but they don't actually pay out. So this hypothesis, which has been sort of accepted on face value in the literature, makes some interesting predictions, which we'll test in this project. There are other sort of non-quantitative hypotheses out there as well, just including them here to be fair. So, perceived skill learning, increased perceived control. I think these are interesting as well. But given that this conditioned reinforcement effect is the sort of the dominant hypothesis, that's the one that I'm going to focus on in explaining the research that we're doing. So there's actually a surprising lack of research showing whether near misses actually reinforce choice. So the studies that have been run to date have used relatively distal behavioural and physiological proxies for reinforcement. So they've looked at things like resistance to extinction. They've looked at things like post-reinforcement pauses, which is this idea that you linger for longer looking at pleasant reinforcing things, and you spend less time on unpleasant things. And then it's been shown that near misses people look longer at, and therefore they are more, the inference is that they are more reinforcing. Whether that's the case or not is unclear. Self-reported motivation to gamble, and then things like facial muscle electromyography, striatal bulb activation, all those sorts of things. However, when people actually test the conditioned reinforcement hypothesis explicitly, they find more mixed results. So this is a really nice paper. Turns out there's a lot of really good gambling research that happens in pigeons. Zentall and Stagner and lots of other people from that field. So there was one study that came out in 2020 that explicitly tested the conditioned reinforcement hypothesis using the sort of like stringent behavioural controls that people who do behavioural research in pigeons often use, and found actually that there wasn't much evidence for a near win effect going on there. So what we're going to do in this study is we're going to collect some trial by trial data where we look at choice behaviour between two simulated slot machines in human participants, and we're going to try and extract a relatively direct measure of the effect of different outcomes on preferences, which is just how often do people stick around with the choice after various outcomes. It's worth saying at this point, this is where I have to acknowledge the slight bait and switch of this talk, which is I'm talking about how it's important to study real world gambling products, and then I just have designed a cognitive task that looks a little more like a real world gambling product. Ideally, well, to one way of thinking, the ideal way of doing this would be to get usage data from the providers and look at how people behave. There's a couple of reasons why that's not feasible here. The main one being that the providers aren't going to share that data with you if you have the sense that you are not just trying to do product design research for them, but you might actually be interested in making submissions about how their product should be regulated. If they have that feeling, you probably will not get the data from Aristocrat or any of the other kind of companies that create electronic gambling machines. So what we're going to do here instead is develop a, in some ways slightly silly, but hopefully somewhat valid behavioral task, where what we're going to do is we're going to ask people to repeatedly play between these two slot machines, giving them cute names. So we have Pelican Payday on the left, we have Bison Bounty on the right. You click to insert a coin, you then see an animation shown on the chosen reel, and then if you get 3 win symbols in a row, you win an amount of virtual coins, which you can trade for payment at the end of the experiment. So we recruited 120 people to do this experiment via Prolific. They each did 120 trials. It's worth saying that although it's presented as a choice task, we actually pre-allocate or pre-randomize an outcome sequence and show it to people regardless of which options they actually choose. So there's no sense in which one of these machines is actually better than the other, but we want to offer them the choice between the two machines because we want to look at when they're switching from one machine to the other as a sort of an behavioral measure of interest. And then we have sequential display of slot machine reels in the following way. So if you see 3 cash symbols here like this, which has a probability of 1/8, the probability just comes from assuming that there's an equal likelihood of a cash symbol in each of the 3 reels. If you see that, then you win 8 coins. That should happen about 0.125 with probability about 0.125. Here's our near miss symbol. So the other thing that can show up here is a club. You can't win with clubs. So if you see bag of cash, club, that would be what we would consider to be a near miss here. Then there's another interesting outcome type, which is where we have 2 win symbols, but where they're not presented in an order that's sort of consistent with the win. So the first one comes down, it's a club. At that point, you know that you haven't won, but you then see 2 bags of cash. And this is kind of interesting and important for the conditioned reinforcement hypothesis, because if you're just looking at the visual similarity of the display to a win, these symbols here have the same visual similarity to a win as the near win. as the near miss. The only difference there is the order in which those symbols are presented. So the conditioned reinforcement hypothesis that's been floating around in the literature for 70 odd years is constrained to make the prediction that the effect of these outcomes on behavior should be the same as these near miss outcomes on behavior. And then we have just the remaining sorts of things that can occur. So this is any time these all have an outcome of 0 coins. They have 2 or 3 club symbols in them. So these are the 8 different things that the person can see. And all we are going to do in this data is we are going to look at, after each of these outcome types, how likely is it that you stick with the machine you just chose? That's a relatively simple measure. Which I'll come back to the video in a second. It's a relatively simple measure because it turns out that this sort of win, stay, lose, shift behavior is a model agnostic signature of reinforcement learning. That is, across a very, very wide range of parameters, across a very wide range of models, associative learning or incentive learning models are constrained to predict that if something good has happened after choosing an option, you should be more likely to choose that option on the next trial than you were on this trial. If something bad has happened, then you should be less likely. And so any simple associative learning process that learns and chooses based on a really simple reward signal is constrained to predict, unless we introduce some sort of exotic assumptions in there, that you should be more likely to repeat your choice after a win and less likely to repeat your choice after a loss. So what we can just do is look, if they chose Pelican Payday on trial T, we'll call that a stay. If they choose it again on trial T+1, we'll call it a shift if they didn't choose that. And then we're just going to look at the rates of stay and shift behavior after these different outcome types in the task. Now I'll show you the videos. This is just give you a sense of what participants are actually looking like here. So here is the near win outcome. So it's about 2 seconds per reel. So close. And then what we have is a non-win outcome, which is timing-wise the same. It also involves 3 symbols, but it's already clear after the first symbol that you haven't won then. Okay. So what we're going to do here is we're just going to have a look at the different outcome types. So we have non-wins, displays with 2 win symbols, the near wins and the wins. And our dependent variable is just going to be how likely is it that you repeat your choice after each of these things. Here is the full data in showing a lot of variability. I'm going to zoom in a little bit and show you what's going on with a y-axis that's a bit more constrained, just so you can compare things a little more easily. So what we see here is that the near wins are in the sort of the light teal blue here. You are more likely to repeat your choice after a near win than you are after a non-win. You're actually even more likely to repeat your choice after a near win than you are after a win itself. So according to a simple interpretation of these data, it suggests that a near win in terms of its effect on behavior is even stronger than winning, which is great if you're designing a slot machine, because this costs you 0, this costs you 0, this costs you 0, this costs you 8 points in that design. So near wins are hugely profitable events to put in there. And then crucially, if you look at the difference between the 2 win symbols and the near win, this is where we have evidence that sort of suggests that the conditioned reinforcement hypothesis isn't sufficient to explain what's going on here. Because, so I haven't shown it here, so 2 win symbols do reinforce choice at a level above the other outcomes. So there is some evidence for the conditioned reinforcement hypothesis. You are more likely to keep playing if you see a display with 2 wins, with 2 win symbols. But when those win symbols are revealed to you as win, win, loss, that's when you see the strongest effect of all. So why might this be? So that was experiment 1. I'll talk now about experiment 2, which is, okay, what's the difference between these 2 things? Well, the same symbols are on the screen, it's just the order in which they're presented is different. And so if it is just the order in which they're presented that's different, maybe one thing that matters is the sort of the sequential display of the symbols. And so what we can do is we run another experiment, which is basically the same in every way, but except whereas in the previous experiment, we displayed outcomes simultaneously, sequentially, now we're just going to display them simultaneously. So here again, here's our sequential near miss. So 2 seconds and a win, 2 seconds and a win, 2 seconds and a non-win. So that's near miss. Here's what a simultaneous near miss might look like. So the timing is going to be the same here because all of these reels are going to spin for 6 seconds. So the total duration is equivalent. But when we see a near win here, it qualitatively has a different kind of character to it. And so if our hypothesis is that part of the effect can be explained by the presentation of a sequence of symbols, then what we might expect to see is that the magnitude of that behavioral near-miss effect might alter in some ways in experiment 2 when we present the outcomes simultaneously. So the overall timing stays the same, the proportions and the payouts and everything stay the same. All we're changing is that whether things are displayed simultaneously or sequentially. And what we see is that basically doing so abolishes the bonus that comes with the near win effect. So we still see that a near win reinforces more than the non-wins. But what we see now is that there's basically no difference between the near win and all the other outcome types that contain 2 win symbols. So one way of explaining this would be to say, okay, there is some sort of conditioned reinforcement effect that's going on here, but that it's even stronger if we allow things to be displayed sequentially. So this is work in preparation. We have a couple more. I was hoping to have a slam dunk kind of result to finish on, but we don't have it. But this will probably end up with 4 experiments in this paper if experiment 4 comes out well, just trying to isolate where exactly that effect is coming from. But if I wanted to just quickly draw a line under that and get to the next portion of the talk, what I would say is that we find that near misses directly reinforce choice behavior. The dominant explanation in literature, which is conditioned reinforcement, can't fully explain the effect. And so if we have a behavioral phenomenon here, where if we're going to develop a satisfying explanation for this, we need some way to explain why the sequence of those informative signals that sort of tiles between the choice and the outcome, why that is changing the effect of that outcome on behavior. I have given myself rather less time than I would like to cover the third part of this. So I might cover this I want to make sure I leave time for questions, but I'm really excited about this research. So I'll spend some time going through it quickly, which is, okay, I'll skip the advertisement. It's quite a fun advertisement, but there is a real world gambling product which is called Instant Cash Out. It was invented in around 2012, 2013. It now exists on all sports betting apps. In the purposes of science, I placed a bet on a baseball game on Friday last week, just for the sole purpose of illustrating this to you. So last Friday, conveniently within my working day, the Kansas City Royals were playing the Houston Astros in Major League Baseball. I placed a $1 stake on the Kansas City Royals to win at a odds of $2.40. So if the Royals win, I get $2.40. If the Royals lose, I lose my stake. It turns out this was a good game to choose because it was kind of an exciting one. So the Houston Astros did win, so I lost my stake. But you can see that the Astros went up 2-0, and then the Royals came back, and then the Astros won again. So if you look at the probability of each of these teams winning as you go through, you see that it sort of fluctuates over time in some interesting ways. And what I'm just going to show you is this feature down here, this button that I can press in the app, which is at any point in time, I can sort of cancel my bet and receive a payout that is roughly proportional to its odds of paying out. So before I place the bet, I can just get my money back. It's kind of like a returns policy. The interesting thing is what happens as the event starts to go on. So here's what it looks like after the 5th innings. So at this point, the Astros are up 2-0, and you can see that my cash out is now no longer worth $1. It's worth 24 cents instead. There will be some kind of calculations that are happening under the hood that specify exactly how that number is arrived at. You can see when the Royals come back and hit the lead, you can see that I'm now being offered more than I originally bet to cash out. So you can think about what the motivations for taking these might be. On the one case, avoiding losses. On the other hand, locking in prospective gains. And then you can see at the very end when it's clear that the Astros are going to win, the cash out has become unavailable, and I can't get any portion of my bet back. So they've locked me into my loss at that point there. So this is also, in some ways, an interesting thing that we can, an interesting kind of decision that we can try and bring under the umbrella of this way of thinking about risky choice. And so here we have informative signals because we're watching the game that we're betting on, but we have an additional option that's not really canvassed in standard models, which is I can just cancel that bet and cash out at any point in time. So this is marketed to gamblers as a way for them to take control of their bets. And it generally lines up with this idea that people find waiting and uncertainty to be aversive and prefer to resolve their uncertainty early if they can. What we are sort of considering here is whether the availability of that cash out choice changes the initial risky choice that you make. So if you know that you will be able to cash out of your bet later, how does that change the way that you appraise the options and bet to start with? So what we basically did, and I will go through some of the details relatively more slowly, so this is our controlled lab cash out task. So prior to seeing the display here, you are told that there will be a display of red and blue cards from which one card will be selected randomly. You say, I predict a blue card will be selected, I predict a red card will be selected, and you're asked how many points you would like to bet on that. That all happens before you see this display here. Then you're shown this display. You click on this timer, which counts down for 8 seconds, and then one card is randomly selected from this array. So that, and then crucially, what we are going to manipulate is whether at the point of making the prediction, you know whether you will be able to cash out later or not. So please make a prediction about the color of the card that the dealer will choose. The cash out option will be available on this turn. So technically, it's offered once during that waiting period, just for a little bit of control. So we tell people this. We ask them what color they predict. We ask them this, and we tell them this, and we ask them how many points they would like to bet. They receive an initial endowment of 3,000 points, and they can sort of cash those out. Cash out is the wrong term, but they receive a payment in response to in proportion to those at the end of the experiment. It's a payment of up to $2, so it's not huge amounts here. I'm perpetually worried about ethics here because technically we are asking participants to gamble on our. I probably shouldn't say that. We are asking participants to gamble on this event. Monash Ethics never had a problem with this, but if anyone from the University of Melbourne Ethics hears this talk, I'm very happy to have discussions about why I think this isn't necessarily problematic. So what happens is you see this, you count down, you have the option to cash out or not. If you cash out, the cards disappear from the screen and you receive your points. If you don't cash out, then you receive a payout. It depends on whether the predicted card color is randomly chosen or not. Just to make this, I've gone through that relatively quickly. So here's a video of someone playing this task. They predict a blue card. They bet 41 points. This is going to be our primary dependent variable. This is a shortened version where it's 5 seconds, so it counts down. You can cash out now for 41 points or wait for the dealer's choice. You can see that the array had sort of an equal number of face-up red and blue cards, so the odds of winning haven't changed there, but I believe that they didn't win there. So here, or they did win, and here they have predicted blue, and they see an array which is inconsistent with the prediction, so that's equivalent to your team going behind, and if you cash out, things disappear from the screen, and you see how much you won. I apologize for going through that relatively quickly. But basically, in this first experiment, we are just going to provide this task to 60 people recruited via Prolific. They're going to do 80 trials in total, 40 in which at the point of making the bet, they know whether they can cash out or not, 40 in which they know they will not be given the chance to cash out. There's some other things happening under the hood, which I'm not going to have time to talk about, which is the likelihood of winning the bet and how that affects the decision to cash out and so on. But the primary variable that is of interest here is just this, the amount of points bet. So you can bet between 0 and 50 points. How much do you bet when you know you can cash out later versus how much do you bet when you know you can't cash out later? I'm going to show you the graph here like this. So you can bet between 0 and 50 points. This is a within subjects manipulation. So when you know you can't cash out, people are sort of roughly in the middle of that range. They're betting about 25 points on average. And then we see this sort of stonking big effect size where people are betting up to about 30% more when they know that they can cash out of their bet later on. And if you look at sort of the overall distribution of bets, what you can see is that it's a uniform-ish distribution when you know you can't cash out, but when you know you can cash out, it sort of pushes everything up against the top end of the range. And so what this suggests is that people's willingness to incur risk, at least if we measure it by the amount of money that they are, or points that they are betting, is inflated by the ability to cash out of a bet later on. So it's almost like if it's a returns policy for my bet, knowing that I can return my bet later on and receive some payment back, licenses me to bet more to start with. And I'll go through this relatively quickly. We basically replicated the finding between subjects design. And this will be the last thing I say about this one. If you look at the decision whether to accept the cash out offer or not, and you look at that as a function of the likelihood of winning the bet, you see some interesting sort of effects. Most notably, okay, so here, 30% probability of winning is you're unlikely to win. 70% probability of winning is you are likely to win. So what you can see is that there's not huge mean differences here. There was a a reviewer asked us to do a quadratic analysis. There was a quadratic effect here. But the one thing I want to point out here is the strong individual variability among individual participants in the background, because this is going to give us a handle on why people might be making this decision. So one reason you might choose to cash out of a bet is because it's a sort of a risk-averse thing to do. You are accepting a certain amount of money now rather than waiting for the outcome of an uncertain event. That is kind of by definition risk aversion. And so maybe it's just, maybe these are all the same people and they're all risk averse. Maybe these are all the same people and they're all risk seeking. The really interesting thing happens is when we look at these individual differences in the 30% win condition, we plot them against these individual differences in the 70% win condition. Contrary to the explanation that this is just risk aversion, what we basically see is that these are negatively correlated with one another. We've done a few different versions of this experiment now. They're not always negatively correlated. Sometimes they are uncorrelated with one another. But if you, in these data at least, the interpretation of these figures is if you're a person who is very likely to cash out when you're behind, you're very unlikely to cash out when you're ahead, and vice versa, which sort of suggests in an interesting way that what's going on here is not just risk aversion, but that people may be appraising the decision to cash out in qualitatively different and sort of individually consistent ways. Okay, I've gone through that very quickly, for which I apologize, but the broad implications of this finding, the reason we're quite interested in it is because this feature is extremely prevalent in contemporary gambling apps. Anytime a bookmaker has a probability model for the event that you are betting on, they will usually offer you a cash out offer. And the mere presence of that feature may be inducing people to place larger bets. So we don't have real world data, but at least in our controlled setting, that seems to be what's going on. This suggests in an interesting way, zooming out, that the initial decision about how much risk to incur doesn't just depend on what's going on at the point of making that this decision, but also depends in sort of interesting and to be elucidated ways on what you will be able to do later on. So the sort of the reversibility or the sort of the optionality of that pre-outcome period changes the way that you engage with that bet at the point of placing it. And as I've said, that we can't explain this using sort of simple risk aversion. So again, apologies for going through this quickly, but that's sort of the general conceptual frame and a couple of the specific things that we are looking at here. And the case that I'll make here is that sort of a more complete theoretical understanding of risky choice is going to require us to move beyond the sort of the simple Drosophila models of risky choice that we use in the lab and try to grapple in ideally in controlled ways, but it won't always be possible, with the sorts of products that exist in the real world that are offered to consumers. And I think the upside of this is that doing so should help us to improve our models of risky choice. And it may even mean that we can make representations that to policymakers and so on that reduce gambling related harm. So if the near miss example would be one case of this, if we can isolate the cognitive mechanism that is responsible for that near miss effect, we are in a position now to make intelligent and informed suggestions to regulators about how manufacturers of slot machines can be allowed to present the display. So near misses and instant cash out have been our focus so far, but there's many other candidates out there. Dan Little's on the call. I know we've talked a little, Dan, about skill-based decision-making and some of those sorts of things. Would love to talk more about that. But more broadly, there's a kind of a menagerie of real-world products that exist. Not all of them are going to sort of slot neatly into this box and arrow framework, but squinting at them and trying to work out whether they do, I think is going to be beneficial for the models in the long run. Okay, so I will thank you very much for your attention. I probably have 5 minutes for questions, so I have to run out. Philip.
Thanks, Dan. Great talk. You mentioned at the outset that none of the traditional laboratory tasks that we use to study decision making would cut. And I think there's a very clear reason for that, is that all of them require people who engage with probability calculus. And we know that that's kind of cognitively ethical, and people are really good at it. And all of the type tasks that you've shown are basically take the probability calculus largely out of the equation. It kind of sneaks back in a little bit with the cashback.
Yes.
And a cashback game could, of course, be implemented as a fair game.
Yes.
But of course, it wouldn't be. And what your results seem to suggest is that the actual expected outcome had a minimal effect on people's willingness to have cash out bets. So it almost sounds as though you've kind of come full circle and said you put the probability calculus back in. People are really not very good at it, and so the casino operator wins from this precisely because although people are doing a calculation of this kind, they're actually not calculating expected values in any useful way. Is that sort of correct summary of it?
I think it's a reasonable explanation for some of it. We have thought about this a little bit. So people are proportionally sensitive to expected value. So I didn't mention this manipulation, but we have a version of the cash out task where we manipulate the expected value of the cash out offer. So sometimes we offer them fair, which, as you say, is possible. Sometimes we take a 10% or a 20% premium. We do see that on average, people are sensitive to that in the sense that they are less likely to, the more unfair that we make the offer, the less likely they are to accept it. So that doesn't suggest that they're doing sophisticated.
Does that kind of percolate right back to their original, their original stage? Because your main finding is that when there's a cash back possibility, people will wager more at the outset. So does that sensitivity, is that sensitivity reflected in the size of the
It's a good question. I don't think we've been systematic enough in the way we've manipulated it to be able to answer that question with the data that we have, because we've typically manipulated it as a factor of the bet that is not known at the point in time of placing the bet. You could imagine doing so, and it would be interesting to know how people would respond to that. This is dodging the question slightly, but one, if you wanted to make a representation to a regulator about what they might do here, one thing you could consider doing is displaying, is requiring, if there's a cash out offer, that the sort of the true or the bookmaker's estimated expected value is displayed alongside it. So you're being offered 24 cents, the bookmaker thinks it's worth 36 cents, something like that. It would be interesting to know how people behave in that case, where in some sense, if you do the work for them, do you abolish this effect? And so it's an interesting question. So if you did see that, then the explanation might be that what's going on is sort of a lack of probabilistic sophistication or something along those lines. I don't think there's an open and shut answer by any means. I will say that what we're seeing is in some ways sensitive to the numerical amount of the cash out offer in a way that makes me think that people are at least trying to do some of these calculations, though of course there's lots of literature that suggests that they're probably not doing it very, very well. I hope that answers the question. Yes.
Hello. I was just wondering about your participants.
Yes.
Are they gamblers?
Really, really good question. No, certainly. So in the we haven't specifically recruited one or the other. What we typically do is we measure gambling status and sort of problem gambling severity as a covariate, and then look to see to what extent it sort of moderates any of the effects that we're seeing. We haven't seen that strongly with the behavioural effects. So, well, I'm skating over some interesting stuff, but the effects aren't huge. For the cash out, it seems to be that people who are the overall effect where there's this inflation of bet amount when you can cash out, that effect seems to be weaker among people who gamble frequently and stronger among people who don't gamble, which is contrary to what we were expecting, but we've constructed a bit of a post hoc explanation, which requires testing. But the post hoc explanation is that this is the sort of feature that might appeal to people who are naive to gambling. So if you are unwilling to gamble because you are someone who finds the possibility of losing money to be aversive, then knowing that you may be able to recover some of your bet if things go south may be more attractive to you and more likely to get you involved in the sort of the ecosystem. That's sort of speculative, but that's what we think might be going on. For the slot machine task, we haven't seen so far any moderating effects of gambling status, gambling severity on the behavior. Where we do see it, and Antonia and I have a paper, Antonia Cholwick and I have a paper under review at the moment, where we do see it is in the strength of the emotional reaction to the outcomes, which is quite interesting. So we see that if you show people these outcomes and then ask them how they're feeling afterwards, we see that people who gamble more frequently tend to have stronger emotional reactions to all kinds of events. So they're happier when they win, they're sadder when they lose, and they're sadder when they see it.
So that's the thing that motivates them to actually go to a casino or something.
Potentially, that would be going beyond the data that we have, but I wouldn't be surprised whether And there's some difficulties in sort of unraveling that. Causally, it may be because they're having stronger emotional reactions because these are more personally relevant stimuli. But certainly that's something that we're sort of interested in exploring as well.